So we were looking at the question as to when a function can be written as an indefinite integral of an integrable function, and we saw that a necessary condition for this was that it should be uniformly continuous and of bounded variation. Today we are going to introduce a new concept which will give us a necessary and sufficient condition for a function to be written as an indefinite integral of an integrable function. And of course, as we have already seen, that this integrable function will be equal almost everywhere to the derivative of the original function. So we are now going to study the concept of absolute continuity. Okay, so definition. So you have f ab to r is said to be absolutely continuous if for every epsilon positive there exists a delta positive, such that given any finite disjoint collection of intervals xk, yk, k equals 1 to n in AB satisfying sigma yk minus xk is less than delta, we have sigma k equals 1 to n mod f of yk minus f of xk is less than epsilon. So let us understand this definition. So you need, given any epsilon, you have a delta. Now uniform continuity will say if mod y minus x is less than delta, then mod fy minus fx is less than epsilon. Now we are going a little further, namely given any disjoint collection of intervals in AB such that the total length of all these intervals is less than delta, then the corresponding variation is also less than epsilon. So it is obvious, so remark, f absolutely continuous implies f uniformly continuous, because you can just take one interval instead of a collection which is less than delta, and then you will have the definition of uniform continuity. So example, f Lipschitz continuous. So then you have mod f of yk minus f of xk is less than equal to L times yk minus xk. This is the Lipschitz continuity. Now if you take k equals 1 to n, sigma k equals 1 to n, okay, so this will be less than L delta. So enough to choose, enough to take delta less than epsilon by L, and then you have, so every Lipschitz continuous function is absolutely continuous. Example, f ab to r integrable and capital Fx equal to f of a plus integral a to x f dm1, then f is absolutely continuous. So you see, it is much more than uniform continuity. We have proved that this is uniformly continuous and bounded variation. Now we are saying it is absolutely continuous, which is a step further than uniform continuity, and therefore this is again a necessary condition for f to be written as an indefinite integral of an integrable function. And we will later see in this session that this is also a sufficient condition. So let us prove this. So if you have interval xk, so xk yk k equals 1 to n disjoint intervals, and sigma yk minus xk is less than delta, so k equals 1 to n. Okay, so now if sigma k equals 1 to n, f of yk minus f of xk is less than or equal to integral over the union xk yk k equals 1 to n mod f dm1. So now we know that the indefinite integral is absolutely continuous. We have made this statement before. By that, what do we mean? Given any epsilon, there is a delta. So given any epsilon, so f integrable, given any epsilon, there exists a delta positive, such that mu e less than delta implies integral mod f over e d mu is less than epsilon. So this was called the absolute continuity of the Lebesgue integral, and this is the reason for calling it that is precisely what we are seeing now, namely the indefinite integral is absolutely continuous in the sense. So if this measure is less than delta, this has to be less than epsilon, and therefore we have the. So this is the reason why we call it. So our aim now is to show that this is in fact a sufficient condition. Now, first proposition is that f ab to r absolutely continuous implies f is bv, and of course that implies f is differentiable almost everywhere. So proof. So you take epsilon equal to 1 and delta as in definition of absolute continuity. So corresponding to epsilon equal to 1, there will be a delta which tells you something happens, and that is precisely we are taking that delta. Now you take capital K equals the integral part of b minus a by delta plus 1. So given any partition P, we can refine it to a partition P dash. So what do you mean by refine it? We are going to add some more extra points such that the intervals of P dash can be divided into K blocks, each with total length less than delta, because K is b minus a by delta plus 1. So if you have K blocks, then each of them will have to be of length less than delta. So you can add extra points, as many as you wish, and then you have this. So now TPF, given any refinement, you can, it's very easy, it's always less than T of P dash F. Now this, if you take in each block the variation, since the measure is total length is less than delta, the variation will be less than 1, which is epsilon. So there are k such blocks, and therefore this is less than or equal to k, and this implies that TAB of f is less than or equal to capital K, implies FBB. So this is the very nice property. So next important proposition. So you have a function f which is differentiable everywhere, and if f dash equal to 0 and the set is connected, then you know that f has to be equal to a constant. Now what happens if its f is differentiable almost everywhere and the derivative is 0? So that's the next proposition. Let f a b to r be absolutely continuous and f dash equal to 0 almost everywhere, then f equal to constant. So if you look at the Cantor function is a function which is differentiable almost everywhere, and the derivative is 0 because almost except for the Cantor set, the complement of the Cantor set consists of flat parts of various intervals. In each interval f is a constant, a different constant, and f dash is equal to 0. So the Cantor function is certainly not a constant, but it is f dash is 0 almost everywhere, and therefore Cantor function is not absolutely continuous. Okay, so that is this. Okay, so now proof. Let C belong to AB arbitrary. Now you take E equals set of all x belonging to AC such that f dash x equal to 0. So by hypothesis, m1 of E equals C minus A, because it is function f dash is 0 almost everywhere. So this measure must be the same as the full measure. Okay, so now eta epsilon arbitrary. Suppose x belongs to E, then what does it mean? F dash x equal to 0. Then for sufficiently small h, we have x plus h will belong to AC, and f of x plus h minus f of x in modulus can be made as small as you like by h, because the derivative is f of x plus h minus fx by h is the difference quotient which goes to 0 because f dash x equal to 0. So it can be made arbitrarily small for h arbitrarily small. So therefore this, and this, you have such intervals and h is arbitrarily small, and this is true. Such intervals form a Vitali covering. And therefore, which has which has finite measure. Okay, so therefore by the Vitali covering lemma, implies there exists xk yk k equals 1 to n, okay, yk equals xk plus hk, okay, disjoint, and such that the measure of E minus union xk yk k equals 1 to n, this can be made less than delta. So delta corresponds to epsilon in absolute continuity definition. Okay, so that is the thing. Now without loss of generality, we can assume xk are numbered in increasing order. Okay, then what do you have? So you have y naught equal to a less than or equal to x1, strictly less than y1, less than or equal to x2, strictly less than y2, etc. Less than or equal to xn, strictly less than yn, less than or equal to c equal to xn plus 1. Okay, so we have numbered it this way, and the strictly less because they are all open intervals, and then they are disjoint, and therefore x2 will be always greater or equal to y1. So this is what we have. Then and sigma k equal to 0 to n of x k plus 1 minus yk will be less than delta. That is coming from this condition here. So these xk plus 1 and yk to xk plus 1, this is the portion which is not covered by those intervals, and therefore you have those, sum of all those is less than delta. So on one hand we have sigma mod f of yk minus f of xk, k equals 1 to n, is less than eta times sigma k equals 1 to n mod yk minus xk, which is less than eta times c minus a. This is just where we have done the Vitali covering from this condition here. Now by absolute continuity we have sigma k equals 0 to n mod f of xk plus 1 minus f of yk is less than delta. So now if you add all these two together by the triangle inequality, so this implies that mod fc minus fa is less than epsilon plus eta times c minus a, and this implies that fc equal to fa and for all c in AB, and by continuity also for B also, and therefore we have that function is a constant. Okay. So example, Cantor function not absolutely continuous. Why? Because Cantor function differentiable almost everywhere, f dash equal to 0 almost everywhere, but f not constant. So now we have the final theorem, okay, which settles this question. So f from AB to R can be written as the indefinite integral of an integrable function if and only if f is absolutely continuous. So proof. So f indefinite integral of an integrable function implies f absolutely continuous, already seen, proved in an example above. We already did this. So now we only have to show the sufficiency. So let f be absolutely continuous. Okay. So it is. So this implies f is BV, implies f equals f1 minus f2, fi I equals 1 to 2, monotonic, increasing. Then f dash equals f1 dash minus f2 dash almost everywhere. And so integral over AB f dash mod f dash dm1 is less than or equal to integral over AB mod f1 dash dm1 plus integral over AB mod f2 dash dm1. But f1 and f2 are monotonic increasing, and therefore this implies the derivatives have to be non-negative. So integral over AB of f1 dash plus f2 dash dm1, and that is less than or equal to, because it's a monotonic function, this is less than or equal to integral f1b minus f1a plus f2b minus f2a, and that is of course finite. So this implies that f dash is integrable. Now you said g of x be the absolute, indefinite integral of f dash dm1. Then g is absolutely continuous. Already seen in the example and also this first part of this theorem. So g is absolutely continuous and g dash equals f dash almost everywhere. This we have seen last time. If you have an integrable function, then the indefinite integral is differentiable and the derivative is equal to f dash almost everywhere. So now if you have some difference of AC functions is absolutely continuous. This you can easily check. All you have to take is the delta to be the smaller of the two deltas, and that will work for you, or you just use triangle inequality. So if f is absolutely continuous, so you write f equal to f minus g, then capital F is absolutely continuous, g is absolutely continuous, implies f is absolutely continuous. And you have f dash equal to capital F dash minus g dash, which is equal to 0 almost everywhere. So this implies f is a constant. So f equals, let us say, f of x equals f of a, and what is f of a? It is capital F of a minus g of a, but g of a equal to 0, and therefore it's equal to capital F of a. And therefore this implies that capital F of x equal to small capital F of a plus g of x, and that is capital F of x equals capital F of a plus integral a to x f dash dm1, and that tells you that it is the indefinite integral of an integrable function. And what is that integrable function? It is equal to the derivative almost everywhere. So function can be written as a indefinite integral of an integrable function if and only if, so this is the final answer, it is absolutely continuous, and the integrand in that case will be the derivative almost everywhere.